This is an extension to the Module 7 slides concerning how FAT file systems work. There have been a few adjustments and expanded the slides just a little bit, so we just wanted to add that. On a FAT file system, the reason that we go over it in class is that it's a good place to start. It allows for the understanding of other file systems, as if you understand this basic file system, you can usually apply those principles to more complex file systems. And it's still in use with small devices, so it's still applicable. With FAT, you've got FAT12, FAT16, and FAT32, with FAT12 being the only thing that ever had a one sector per cluster ratio and was only ever used on floppy disks. And you have some other versions of FAT today as well, but those were the first. And what defines a FAT file system is that it uses a file allocation table, and of course it's proprietary to Microsoft. On a FAT file system, you have two types of clusters. Now, we've seen in previous exercises what lies in the cluster, but what we've been looking at is file contents. Well, clusters on a disk are used to hold file contents and file system structures. And in the case of a FAT file system, you have two different types of clusters. You have data clusters, which we have already seen, that holds file contents. And then you have directory listing clusters. Clusters that hold directory structures for the FAT file system. The directory clusters hold directory entries. A directory entry holds the file system metadata for all the files, for a file, which includes the file names, its timestamp, and the starting cluster for the file. The starting cluster and the starting cluster only. A cluster used for directory entry will not be used for anything else. It will be assigned as a directory entry structure. At the very beginning of the disk, you have a special cluster which holds the first directory listing cluster, which is normally called the root directory. So if we were to kind of picture this root directory structure, what it would have in it is some file names, followed by timestamps, followed by a starting cluster for each file. Now, if we were to follow, let's say, the file 1 directory listing, if we were to go to cluster 4 to see what's there, what we would actually find would be the contents of file 1. Whether it's text or colors or whatever it is what we would find in file 1, or in cluster 4 in this case. So all files are found by starting in this root directory. And that's because you can have a directory entry for a file name or the directory entry for a folder. So if we were to follow, let's say, folder 1 to cluster 7 to see what's in there, we would see that in cluster 7 you have more of these directory entry structures. Now, other than the root directory, every directory entry has two special files in the very beginning. A dot file and a dot file. The dot file, and neither of these actually have any contents, they just have directory entries. And the dot file has a timestamp in it, and then has a cluster location for the current location. You'll see folder 1 here starts in cluster 7, and the dot file starts in cluster 7. That's just a way for the computer to know, or the operating system to know, where it's at. The dot file is always going to be the parent directory. The cluster that contains a directory entry for the folder itself. So in this case it would be 0 because it's the root directory. So then we have file 3, which has a timestamp and a starting cluster. And we have another folder within this folder called folder 3. So if we were to follow this folder to its cluster and see what's in that cluster, we would find more directory entries. This time the dot file would contain 11 because that's the cluster location for this set of directory entries. The dot file would hold cluster 7, as that's the parent directory for this folder, or for this set of directory entries. That's all a folder really is a set of directory entries. And then it'll contain whatever files and folders that are in that directory. So if we were to follow folder 4 in this case, once again we would have a dot file which has cluster 13 as its starting location. so that the operating system knows where it's at, and a ... a previous locator, so that it can go back and forth within the directory listing, know where it's at, know where it's been, etc., etc. So, and then it's going to have whatever files and folders are in that directory. So we just keep going on and on and on until we run out of subfolders. So every time a folder is created, essentially a cluster is assigned to that folder, which contains directory entries for whatever's in that folder. Now you may have noticed that in the root directory, in our little depiction here, we went straight from 4 to 6, and in our folder 1, which was located in cluster 7, we had a file 3 and 9 and a folder 3 and 11. So what's in cluster 5 and what's in cluster 10? Well, most likely file 1 needed clusters 4 and 5 to contain its data, and file 3 needed clusters 9 and 10 to hold its data. But how do we know that? Well, we don't. The only thing that's in a directory entry in a FAT file system is the starting cluster. The way that files are put back together involve the FAT table. The FAT table is in a special location at the beginning of the disk, which contains a map. And this map maps out all the clusters on the system by cell. It's a big table. In the cells of this table, you'll have either a 0, which means unallocated. You have a series of F's followed by a 7, which means bad cluster. Or a series of F's followed by 8, or you'll notice that in our FAT32 thumb drives that we use in class, they actually end in 0. That's fine. And this symbol means end of file. And all of the values mean that cluster is allocated. For example, we have alice.txt, which has a starting cluster of 3. So if I count here, 0, 1, 2, and 3, FFF8, I said was a end of file. This means alice.txt starts and ends in cluster 3. go.jpg starts in 4. So we're looking 4 and we see a 5. So from 4 you go to 5. From 5 you go to 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. From 8 you go to 9. At 9 you go to 10. Remember the hex value A is actually a 10. And at 10 we have an end of file. So go.jpg is stored in clusters 4, 5, 8, 9, and 10. Tag.doc is in 16. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is 16. The 16 says go to 15, and 15 has 0. But what did I say 0 meant? 0 means unallocated. This file is corrupted. It doesn't have a link, and it would not be opened successfully. In the in-class exercise, which is a different video, we'll actually load up a thumb drive with some files, show what the directory listings look like, follow some of those around, and then interpret a FAT table in a similar way that we just did in this presentation.